Thank you. Can you hear and see the slides?
Yes.
Okay. Good afternoon, everyone. And first of all, thank you to the SAZERAC team for giving me a chance to present our results. And thanks for organizing such a nice conference in such a short time. So today I'm going to talk about how to infer something about cosmic reionization using Lyman alpha emission. And this is a work done with collaboration of many people. I am a postdoc in University of Geneva. I work with mainly Anne Parham, who is also in Geneva. The other people, Thibaut, Jeremy, and Joachim, they work in Geneva and in University of Lyon. So this audience needs no introduction to the cosmic reionization. So here we all understand that it is important to understand the sources and the process of the reionization, but unfortunately, due to increasing IgM opacity, it is very hard or almost impossible to directly detect the ionizing photons around Z is equal to 6. So we need some indirect tracers for the ionizing radiation or the Lyman Continuum emission. So in this work, I will focus on Lyman alpha as that indirect tracer, although some other tracers have been discussed in literature in recent years. So in past few years, observers have seen that if we are able to measure the escape fractions of Lyman alpha and the escape fraction of Lyman continuum, we see that there may be a correlation between the two. So these are all data from local Greenpeace galaxies where it was possible to measure this quantity, the Lyman continuum. So this is an interesting correlation, and it begs the question, can we use this in the reionization era? So to answer that question, we need to know, does this correlation hold around Z is equal to 6 and higher redshifts? And does this hold for all galaxies, since we don't have a very big sample in observations yet? And then we can also ask that if it does, if there is a correlation, then given the Lyman alpha properties of the galaxy, such as their escape fraction, can we then calculate Lyman continuum properties, such as Lyman continuum escape or Lyman continuum luminosity? So since these quantities are hard to actually observe in Z is equal to 6, it is a great idea to explore some results from simulations. So here we use the SPHINX simulation. And this morning, Matthew already gave a little of introduction about the SPHINX. So in very short, this is a radiation hydrodynamical simulation. It has very high spatial resolution of about 10 parsec. The box size is 10 megaparsec. It's a Ramsey RT code. And the simulation runs till Z is equal to 6, and it has reionized the universe by then. So here, for doing the Lyman alpha calculation, we post-process the galaxies in the SPHINX simulation using code called RASCAS. This is a new public code, which is open for anyone. And I encourage you to all go and check this out. So here we take each of the galaxies and then run the radiation transfer using both recombination process and the collision process. So for each halo, we run it twice for these two processes, and we employ 10 to the power 5 photons for each. And we here consider the halos which have stellar mass more than 10 to the power 6 solar mass. So the halos in these high redshifts have complicated geometries. Here you can see one example. This is the stellar distribution, and this is the gas distribution of the same galaxy. So lots of satellites are roaming around, and interactions and often mergers also happen. So the quantities that we will describe next, these are all global quantities, and the production of the Lyman alpha and the propagation of the Lyman alpha is happening till the halo virial radius here. So we don't take into account IgM in the next results that I'm going to show. We have galaxies at different snapshots, and we tested and found that the properties of the galaxies at different redshifts, 6, 7, 8, 9, and 10, are not very, very different. They are similar in physical, Lyman alpha and Lyman continuum properties. So we stacked them together to get better statistics. So in the end, our sample size is 1933 galaxies. So coming to results, the first is luminosity. The intrinsic luminosity of Lyman continuum correlates quite well with Lyman alpha, as we see here. This is a good correlation, and this is to be expected because both of them depend primarily on the star formation rate of the galaxy. And if we look at the escaping luminosity or the output luminosity for both of them, there is still a correlation, but there is a greater dispersion here, especially for the fainter galaxies. Coming to the escape fraction, we started with that observational plot of the escape fraction, and the observational plots are here in blue. So we plotted all of our galaxies here, and some of them are very faint. And we find that if we plot all 1900 galaxies, there is basically no correlation here. It is scattered everywhere, and we can in general only say that Lyman alpha escape fraction is greater than Lyman continuum escape fraction. This is the one-to-one relationship line. So we asked that, okay, what if we just took brighter galaxies? So we took, say, a cut of 10 to the power 39 arcs per second, and then we still have a very scattered relationship. But if we go towards more bright galaxies, such as greater than 10 to the 41, it seems like there may be a correlation which matches our observations. So we think that the observed positive correlation of the two escape fractions may be a selection bias, which holds true only for the brightest galaxies. So we find that at different luminosities, galaxies can have very different escape fractions. But it is often useful to know what is a typical escape fraction or a median escape fraction. So here we divide our sample according to their Lyman alpha output luminosities. So we bin them, and in each bin we have this many galaxies. So the median, and then we plot the median value of the escape fraction of Lyman alpha and the escape fraction of Lyman continuum. And we find that in faint galaxies, both of the escape fractions are very high, basically 1. And then both of them drops. It is seen that Lyman continuum has a kind of similar escape fraction for a large range of Lyman alpha luminosity, and around 10 to the power 41, 42, which is mostly interesting for the current observational limits. The Lyman continuum escape fraction is around 10 to 15%. And for Lyman alpha, it hovers around 30% here. So this may be interesting for observers. We can also ask the question that what is the total contribution to reionization for these different groups of galaxies? So for different bins, we sum up all the Lyman continuum luminosities of all of the galaxies here, and then we plot that total output here. So we see, first of all, that this is the good statistics region. We have few galaxies here and few galaxies here. And we see that the very faint galaxies contributes less to reionization. They have very high escape fractions, yes, but they are so faint that the total number of ionizing photons that escapes these systems is not very much. And the ones that are brighter, their escape fraction is low, but the luminosity is high. So with these two, it turns out that these ones contributes more ionizing photons to reionization. So till now, I talked about the total escape fractions. So if we look at their sky maps or the Hill-Pix maps, say of two galaxies, we see that the Lyman alpha escape fraction map and the Lyman continuum escape fraction maps, they are very anisotropic. Some regions are very bright and some are quite dark. It is also seen that the places which is bright for Lyman alpha is also bright for Lyman continuum. So the escape directions of Lyman alpha and Lyman continuum seem to be highly correlated. And I think someone asked this during Matthew's talk. So yeah. So in the last part, we asked that, okay, we did not see any one-to-one easy correlation between escape fractions of Lyman alpha and Lyman continuum, but given that we have a lot of data, can we predict Lyman continuum properties given all the other galaxy properties that we have? So this part of the work is inspired by work done by Axel Ranholms and Matthew Hayes, and I think Axel is giving a talk in the next session. So here we are doing a multiple linear regression method where this is kind of a formula that we are trying to apply. So Y is something that we want to predict, such as Lyman continuum luminosity. And then different X are different galaxy properties that are available to us, such as their physical properties and their Lyman alpha properties. So then we try to fit such kind of relation and see if we can recover the actual values of Y. We can also then ask that if this relationship holds, then which one of the X's are most important. So here are the values that are observed in simulation. This can be called as like true values. And these are the prediction from our model. So the first, we are trying to say predict the intrinsic value of Lyman continuum luminosity. The input here are galaxy properties, that is their gas mass, stellar mass, dust mass, their sizes, stellar age, metals, and their star formation rate. So we find that the predicted value and the actual values match quite well. The R-square is a measure of how good the model is, and if it is close to 1, that means that the model is pretty good. So we have R-square of 0.87 here. For the escaping luminosity of Lyman continuum, we can give an input of the same galaxy properties, plus we also give Lyman alpha luminosity, and we get a R-square of 0.80. And for the finally, for the escape fraction of Lyman continuum, we give input of the same 2, plus we also give escape fractions of Lyman alpha, and we get a R-square of 0.69 here. And then we can say that, okay, so what are the most important X variables for this? It turns out that to predict the Lyman continuum intrinsic luminosity, star formation is the most important quantity. Just the 2 star formation rates, the instantaneous and the long term, can explain 84% of the variance in the data. For the escaping luminosity, if we know the Lyman alpha luminosity and gas mass, it can do the job quite well. And finally, for the Lyman continuum escape fraction, knowing these 3 things can give us a 70% explanation of the variance. So to summarize, we need indirect threshold for Lyman continuum radiation, and we're asking if Lyman alpha would be helpful. So we analyzed 1933 galaxies, and we find that the intrinsic and escaping luminosities are well correlated for Lyman alpha and Lyman continuum. Their escape fractions are correlated, but only for brighter galaxies. And we do a multivariate regression modeling, and we find that it is possible to predict Lyman continuum given the physical and Lyman alpha properties. So Lyman alpha can be very useful to select Lyman continuum leakers. Thank you.
All right, great. Thank you, Moupiya. So time for questions. So Melema Garrett is asking that, what is the physical cause of the rapid change in the median F escape Lyman continuum around a Lyman alpha luminosity of 10 to the 38th arc per second?
Yeah, this I need to look into this more. These ones have very low statistics, so we can maybe ignore this ones, but yeah, I would need to look into more what happens here. Good question. Thank you.
Okay. So the next question is from the Thomson. Are escape fractions related to burstiness of the galaxies? If so, do ionizing luminosities depend on the nature of the ionizing stars? BPAS model, Chabelier IMF say thank you.
Yes, it does. Yes, it does. So I think Matthew has done more work on that aspect, and he found that yeah, the burstiness of the star formation definitely has an effect on the total Lyman continuum escape from the galaxies, and it also follows the cycle of the star formation burstiness in a given galaxy.
Okay,
so
so
yeah,
one. Good. So the one last quick question from Matthew Hayes. What is the resolution of these simulations, especially in the CGM? And what do the Lyman alpha spectral profiles look like?
Oh, the Lyman alpha spectra, I do not have an example, but I can post on Slack one or two of them. The resolution is around 10 parsecs in the highest resolution area, and the mass resolution is 1,000 solar mass for stars.
Okay, great, thank you.